This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 7, Weak Bases. Now that you should have a good understanding of weak acids, weak bases are very, very similar. So you're going to learn that the ionization of a weak base in water is in equilibrium with that constant of Kb that can be used to calculate the pH of a weak base solution. Now let me remind you that pH, even though they're always asking for the pH value, we really need to calculate the pOH of a base solution because bases have hydroxide ions in it, and then we have to work from there to calculate the pH. So most problems, whether they're acidic or basic, they're always asking for pH, so we have to keep that in mind. Thought that was cute. Anyways, pause the video, fill in the words, and then play to hear my words. So a strong base is going to be the same as a strong acid, 100% dissociates. Now, these are just 3 of those strong bases, but you know you have that list and should have those memorized. And a weak base is the same as a weak acid. It is less than 100% dissociation. So we have this weak base in our water, and now we have that conjugate acid. So we have that base conjugate acid base pair, and we have that hydroxide ion in it. So our Kb is the same as Ka. It's the base dissociation constant, and this is an equation that you want to make sure that you have memorized. You're going to see this ammonia often, and it's a difficult one to understand because the ammonia itself as the base does not have hydroxide in it, but when the ammonia reacts with the water, again, it's a base because it takes that H plus and forms that ammonium polyatomic ion, and then you're left with those hydroxide ions in there as well. So that's a really important reaction to kind of get into your head. So let's look at an example. These are just problems like we've seen before, but again, we want to remember that we're calculating the pH of a solution even though we're talking about the base. So we first have to figure out the pOH. And the other thing to keep in mind is that we have 2 hydroxide ions. So let's look at the reaction, right? We know that calcium hydroxide is strong, so that's going to be easy to figure out. It's going to completely dissociate in water, but we're going to have that 2 hydroxide ions. So keep that in mind. So we have calcium hydroxide completely breaking apart, so we have a regular arrow, into Ca plus 2 hydroxide ions. Well, what does that mean? Well, if we have 0.011 molar of the base, it's going to completely dissociate. So we're going to multiply it by 2 in order to get the amount of hydroxide ions. So 0.002 molarity for that hydroxide ions. Now remember, let's solve this problem. I like to do it this way. pOH is going to be the negative log of 0.022. Should be very familiar to pH, right? pH equals the negative log of your H plus concentration. pOH is going to be the negative log of your OH concentration. Okay, so we're just plugging and chugging here. So we get 14 minus that 1.66 of our pH, and then we get 12.34. So that should make sense, right? If it's an base, it should be greater than 7 on the pH scale. Now, we could also do it this way. Remember that equation? H plus times OH minus gives us this Kw, right? So we could also plug and chug there. So our H plus concentration is going to equal the Kw divided by the OH negative concentration that we just found in our equation. And we can plug and chug. We could do the pH of the negative log of the value of the H plus concentration, and we get the same number, get the same exact number. So we want to just keep that in mind, that you can do either one. I personally just like to do the pOH and subtract from 14, but that equation it works as well. So let's look at example 2. Now we need to calculate the pH of a weak base. And again, this weak base reaction is one that we really need to know. And now they have to give us a Kb. So again, there's no liquid in here, right? There's no water. So even though that ammonia reacts with that water, we're not going to include it into our Kb expression, okay? So now we need that chart, right? That ice chart. So here's our ice chart. We initially started with 0.006. We didn't have any of the ammonium or the hydroxide ions. We don't know what the change is because we don't know what the values of the ammonium or hydroxide is in solution. So we're going to use that X like we've seen before. So we kind of plug and chug and try to solve, right? So we have the 1.8 times 10 to the negative fifth, which is our constant, equals X squared, each of those in equilibrium, divided by the 0.006 initial value of the ammonia minus X. But now remember, that's going to be so small, we're just going to get rid of it. So X squared over 0.006, again, rearrange, X equals 3.3 times 10 to the negative fourth molarity. Again, what does this represent? This represents the hydroxide ion. So now we can just plug it into our POH equals negative log of our OH minus concentration. Remember, we need to subtract that POH value from 14 to get an answer of 10.52. So really the only difference right now from a weak acid to a weak base is solving for the OH minus concentration, the POH, and then subtracting it from 14 to find the actual pH value that they're looking for. And again, this should make sense. 10.52 represents a base solution. So we could also do it this way using that KW again. Again, just showing you a different way of doing it, rearranging, since we already have that 3.3 from the previous slide there, and we have that 3.0 times 10 to the negative 11, molarity 4 now, we're solving for the H plus concentration right away. Again, pH, bada bing, bada boom, and you get the same thing, 10.52. So there are a couple different ways to go about these problems. You just have to decide which way is easier for you. See you in class and do some bookwork.